In section 5.2. All right, so before we have a couple of theorems that we're going to talk about. Let's remember what these words that we're using, what they mean. Perpendicular. What do we mean by perpendicular? When two segments are perpendicular, or a line is perpendicular to a segment, what do we mean? Yeah. The angles are congruent, and there's a special angle. Perpendicular means they make 90-degree angles. So we have the 90-degree angles, and then our slopes would be negative reciprocals. So there's a relationship with the slopes as well. And bisector, what do we mean by bisector? What does a bisector do? Cut something in half. So we're talking about perpendicular bisectors, something that meets a segment, something at 90 degrees and cuts it in half. Angle bisector, something that cuts an angle in half. All right, so our first theorem, perpendicular bisector theorem. So what the perpendicular bisector theorem tells us is that if a point is on the perpendicular bisector, of a segment, then it is equidistant from the endpoints of the segment. Now this word equidistant, what are we going to, what does that mean? Equal, distant, distance. So what we're saying is if a point is on the perpendicular bisector of a segment, then it's the same distance from the endpoints of a segment. Ms. Lindgren, Carly was very happy that you finished copying the algebra reviews. See, that's what Ms. Lindgren has in. Yeah.
Hopefully the rest of you feel the same as Carly.
I'm pretty sure that was mutual. All right, so what we're saying here, that's the feeling that I got.
Right.
Just definitely a bunch of warm and fuzzy feelings in here.
Rare in this round.
All right, so there's our segment AB, and the endpoints of our segment are A and B. And here's a point P on the perpendicular bisector. So we'll draw it like so.
Actually, I have both copies, Carly. I ordered these and for 15 minutes.
So there's our point P that's on the perpendicular bisector. We know this is a perpendicular bisector because we have a 90-degree angle there, and the segment's cut in half. So we're saying that, I'll call this point M. So line PM is perpendicular to segment AB. And line PM, no, that's already, the AM and MB are congruent. Then If I draw in these segments, I'll do that in dotted line. Don't need an arrow here. Do it in blue. If we draw the segments, didn't want the arrow. Get rid of that arrow. There we go. If we draw in those segments from A to P and B to P, those are going to be congruent. Segment AP is going to be congruent to segment PB. So if this point P is on that perpendicular bisector, the distance from P to A and from P to B is going to be the same. And this is why when we did our constructions for the bisector of a segment or the perpendicular bisector, when we set our compass open more than halfway and made our mark, and we kept the compass the same and came to the other side and made our mark, the compass being open the same made sure that those marks where they met there are the same distance from the ends of the segment. So that's really why that construction works, is the compass is making sure we're the same distance from the endpoints of the segment. And we can write the converse as well. And remember that the converse just means we switch the order of our if and our then. So our converse is going to say if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector. Perpendicular bisector. Remember the little upside down T means perpendicular. So what we're saying here is if we have a segment AB, and we have a point P up here, and we know that the distance from A to P and B to P are congruent. So we're saying if AP is congruent to PB, then if we draw this segment down the middle, like so, oops, undo one of those. If those are congruent, then this point, if we draw the segment here to point M, then line PM is going to be perpendicular to segment AB, and AM is going to be congruent to segment MB. Yeah. Yeah. Now for this one, if we wanted to prove this, what we would do is we would draw that segment down the middle, and then we would say, we would draw the perpendicular segment down the middle. We'd say that segment's congruent to itself, so these two triangles are congruent by hypotenuse leg, so these two segments have to be congruent. All right, questions about our perpendicular bisector theorem? What we're going to do next time is talk about what happens when we make the perpendicular bisectors of all the sides of a triangle. So we make 3 perpendicular bisectors. Something special happens in that case. So let's take a look at one of the kinds of problems that you might see that has to do with perpendicular bisectors. So here's our setup. So I'm going to mark my triangle like this. This tells me, before I write anything else down, that that segment is the perpendicular bisector of the base of the triangle. So if I call this N, P, M, that point O, and I say this is 6x minus 1, and this is 3x plus 8. And we want to find the length of MN. And remember, when we write the two endpoints of a segment without anything over the top, that means we're looking for the length. Well, we know that MO is the perpendicular bisector. Of NP. Well, what does that tell us about point M? It's on the perpendicular bisector. How are these two distances related? They're the endpoints of my segment. M is on the perpendicular bisector. So how are these distances related? What did our theorem tell us? Point on the perpendicular bisector is the same distance from the endpoints of the segment. There's my distance here. There's my distance there. So MN has to equal MP. And that tells us that 6x minus 1 has to equal 3x plus 8. Add 1. 6x equals 3x plus 9. Subtract 3x. I get 3x equals 9, and x equals 3. Well, the question doesn't say find x. It says find mn, this distance. So I plug that in. 6 times 3 minus 1. 18 minus 1 is 17. What should the length of MP be? It should come out the same, right? We said those lengths are the same. Well, 3 times 3 is 9, plus 8 is 17. So we could check our work that way. Those two should come out the same. So that's an example of the type of problem you might see. All right, questions there? Okay, we need a reminder. We're going to do a reminder, and then we'll talk about our next theorem. The distance from a point to a line. So if I have a line here, and I have a point, and I want the distance from that point to the line. So there's that, and there's P. Which direction from point P to the line am I going to go to find the distance? So, kind of in other words, if I wanted to know the distance from where I'm standing to the back wall, how would I figure it out? Would I walk, so the back wall, this over here is part of the back wall. Would I walk from here to the back corner? Would that tell me the distance? No. What do I want to do? Straight. We want to walk straight towards the wall. What do we mean by straight? How do we say straight in math words? If I walk towards the wall, what angle does my path need to make with the wall for me to be walking straight towards it? 90 degrees. So the distance from a point to a line or a point to a segment is the perpendicular distance. That's our distance. We can't just go any old direction. We want to go the shortest distance, the perpendicular distance. That's how we make sure that we get the shortest distance. All right, so now that we have that, this is important for our next theorem, the angle bisector theorem. The angle bisector theorem tells us about a point on an angle bisector, as we might guess from the title. So if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. And we've been using this idea when we talk about angle bisectors. We've been using it intuitively. A segment that cuts an angle in half means we're halfway between the two sides of the segment. Well, halfway between means we're the same distance from each side. So that's what this theorem is telling us, that if we're on the angle bisector, we're the same distance from each side of the angle. So let's draw, if we draw a picture here, here's my angle. And I'm going to call this angle PQR. And I'm going to draw the angle bisector. So this ray is the angle bisector. And I'm going to say if ray QS bisects angle PQR. This should be a P. Sorry. And so I'm going to draw the perpendicular distance from S to the sides of the angle. And PS is perpendicular to ray QS, and SR is perpendicular to QS. Then what that tells us is these two segments are congruent. So if we're on the angle bisector, we're the same distance from the sides of the angle. We can also say the converse of this theorem. The converse, we just switch the if and the then. If a point is equidistant from the sides of the angle, then it is on the angle bisector. So what this is saying in pictures is if we draw our angle and we have some point here that's the same distance from the sides of the angle. And remember, our distance has to be the perpendicular distance. Call this S, P, Q, and R. And we know that those are congruent. If PS is congruent to RS, and these are perpendicular, if that is the case, then if we draw the segment from the vertex of the triangle through point S, or the ray or segment, either one works, then ray QS bisects angle PQR. So we would know that those are congruent. And I realized I wrote the wrong letters up here. This should be perpendicular to QR and QP. So if our point is equidistant from the sides of the angle, then it is on the angle bisector. If we draw that segment in there, it bisects the angle. And next time we will talk about what happens when we draw all three of the angle bisectors of a triangle. Some nice things happen. Some special things happen. All right, so let's look at one example having to do with angle bisectors, and then we'll be set for today. Here is our setup. All right, so before we're even given any other information, the fact that we have this figure marked like this tells us that this ray is the bisector of this angle. It cuts it into two equal pieces. So we'll call this triangle or this angle LMP. And I'm going to draw in some more segments here. And we're going to say those are 90-degree angles. And we're going to say this segment is 6x, and this is 3x plus 12. Well, we decided already, and what the problem wants us to do is find OP. So before we added any other information, we figured out that LO, ray LO, is the angle bisector. From the information that we're given, just the fact that those two angles are congruent, that tells us that that's the angle bisector. So we know, and these are perpendicular, these segments are perpendicular. So what do we know about these two distances? They have to be the same. They have to be the same distance from the side of the angle. So MO has to equal OP, and 6x has to equal 3x plus 12. Subtract 3x. 3x equals 12. Divide by 3. X equals 4. And the problem says find OP. OP equals 3 times 4 plus 12. 3 times 4 is 12, plus 12 is 24. And we can check 6 times 4. 24 also. So those two come out to be the same, which is what we knew should be the case. All right, questions? Okay.